Covalent bonds are formed by atoms when they attract each other's electrons into their own valence shell. This creates stable arrangements. When covalent bonds are formed, atoms share electrons instead of transferring them to have full outer shells. Covalent bonds only occur within nonmetals. This is because of the differences in electronegativity. These differences in electronegativity bonds can fall into two categories, polar and nonpolar. Hydrogen bonds fall into the polar category due to its higher differences in electronegativity between atoms. Here we have ammonia, which is represented by one nitrogen atom and three hydrogen atoms. The three electrons supplied by the hydrogen atoms share their electrons with the nitrogen. Covalent compounds such as ammonia tend to have lower melting and boiling points, as the bonds are held by weaker intermolecular forces. Due to this, they require less energy to break down and separate. These bonds also cannot conduct electricity. This is because the molecules are neutral and there are no free charges in the ions to move around and carry electrical charge. Non-polar covalent bonds differ to polar covalent bonds in which its electronegativity is less than 0.5 or if they are the same. When this occurs, the electrons are shared evenly. Here we have ethylene, which is an example of a covalent nonpolar bond. As you can see from the drawn diagram, the nonpolar bonds also share electrons like the polar bonds. Nonpolar bonds have very low melting and boiling points as they have weak attractive forces to each other. Since the forces are weaker, they require less energy to break apart. Unlike polar molecules such as ammonia, nonpolar molecules cannot easily dissolve in water. Polar solvents can only dissolve polar solutes because of the attraction of opposing charges between the solute and solvent particles. However, nonpolar solutes can only be dissolved by nonpolar solvents since they cannot attract dipoles or ions. Due to this, nonpolar molecules are unable to dissolve in polar substances such as water. Ionic bonds occur between metals and nonmetals and form by transferring electrons to each other. Ionic bonds tend to have larger crystal structures in solids instead of discrete molecules like in covalent bonds. This is because of the opposing electrical charges, which cause the ions to bond very tightly together. Here we have sodium fluoride, which is represented by sodium cations and fluoride anions. The atoms transfer their electrons instead of sharing them, which is shown by the drawn diagram. Most ionic substances are soluble in water because the ionic compound can dissociate into its ions, meaning that when sodium fluoride is dissolved into water, it will dissociate into sodium and fluoride ions. This is because water is polar. The negative dipoles of water stabilize the sodium ions, and the positive dipoles of water stabilize the fluoride. In a solid state, ionic compounds cannot conduct electricity. This is because their ions cannot move since they are in fixed positions. However, in water, ionic compounds can conduct electricity through its free floating ions, which allow them to conduct electrical currents. Covalent compounds may exist as molecules as well as covalent networks. Covalent network can be made up of either one or two nonmetals and have strong covalent bonds. Their atoms are bonded to its closest neighbors and have no delocalized electrons, which are electrons in atoms, ions, or molecules that do not belong to an atom or covalent bond. Here is a structure of silicon dioxide, and as you can see, it has a diamond lattice shape, and its atoms are linked together by strong covalent bonds. Covalent networks have high boiling and melting points because their bonds are much stronger and there are more of them. Covalent networks also have poor electrical conductivity. This is because their electrons are not delocalized and not free to move around. Metallic bonding only occurs amongst metal atoms. In these types of bonding, the electrons are free to move and are delocalized. This can be described as an electron seam model, as the electrons in metallic bonds stay apart from each other and are repelled. Because of this, they are constantly moving. Its structure is held by strong electrostatic forces between the metal cations and sea of valence electrons. Here is a model of aluminium, and as you can see, the electrons are far apart from each other due to its repulsion. Aluminium has a crystalline lattice structure which is closely packed together. The electrostatic forces of attraction hold the positive cations in its structure. Since the electrons in metallic bonds are delocalized, they can move through the lattice in all directions. When force is applied onto metallic bonds, the bonds do not break, but instead the nuclei shift, causing ions to slide over each other changing its shape without shattering. Metallic bonds are good conductors of heat and electricity as it relies on the flow of electrons. As mentioned earlier, electrons in metallic bonds are constantly moving around, allowing electricity and heat to easily flow through.